Welcome back. Now that we've covered the exploratory data analysis, I'll discuss the implementation and model testing. The machine learning model I have chosen to implement is called ARIMA. ARIMA is a forecasting algorithm based on the idea that the information in the past values of the time series can alone be used to predict the future values. The AR stands for autoregression, which is a model that uses the dependent relationship between an observation and some number of lagged observations. I stands for integrated, which is the use of differencing of raw observations, subtracting an observation from an observation at a previous time step in order to make the time series stationary. And MA stands for moving average, which is a model that uses the dependency between an observation and a residual error from a moving average model applied to lagged observations. An ARIMA model is one where the time series was differenced at least once to make it stationary, and you combine the AR and the MA terms. The model in words is your predicted YT equals your constant plus your linear combination lags of Y up to P lags plus the linear combination of lagged forecast errors up to Q lags. So the first step to build an ARIMA model is to make the time series stationary. Why? Because the term autoregressive in ARIMA means it is a linear regression model that uses its own lags as predictors. Linear regression models work best when the predictors are not correlated and are independent of each other. Now that we have a basic understanding of an ARIMA model, I will explain the model parameters. An ARIMA model is characterized by three terms or parameters, ARIMA P, D, and Q, where P is the order of the AR term, the number of lag observations included in the model, also called the lag order. Q is the order of the MA term, the size of the moving average window, also called the order of moving average. D is the number of differencing required to make the time series stationary, the number of times that the raw observations are differenced, also called the degree of differencing. So, a linear regression model is constructed including the specified number and type of terms, and the data is prepared by a degree of differencing in order to make it stationary, which is aimed to remove trends and seasonal structures that negatively affect the regression model. A value of 0 can be used for a parameter which indicates to not use that element of the model. That way, the ARIMA model can be configured to perform the function of an ARIMA model and even a simple AR, I, or MA model. If a time series has seasonal patterns, then you need to add seasonal terms and it becomes a SARIMA model, short for seasonal ARIMA. Our objective is to identify the values of P, D, and Q, but how? Let's recall the visualization from our exploratory data analysis of the number of 3-on-1 calls made per day in 2020. First, we will look at the D, the number of differencing parameter. The first step to building an ARIMA model is to make the time series stationary. To check if a series is stationary, we use the augmented Dickey-Fuller test from the stats model package. For an ARIMA model, you need differencing only if the time series is non-stationary. Otherwise, no differencing is needed and D equals 0. If your p-value is greater than 0.05, we go ahead with finding the order of differencing. Our p-value was 0.346, which is greater than 0.05, so we will proceed with order differencing. This slide shows our original series, the same image from the prior slide, and its autocorrelation graph in comparison to first order differencing and its autocorrelation graph. First level differencing achieves a p-value of 0 and an autocorrelation graph that stays relatively within boundaries. However, we can see that every 7 lags go outside of the boundary, which shows a weekly seasonality in the data. Because of this, we need to implement SARIMA, which stands for seasonal ARIMA, to take care of this. If the model has well-defined seasonal patterns, then we'll enforce D equal to 1 for a given frequency of X. Because we could see clear weekly trends in our autocorrelation plot on the previous slide, we need to account for seasonality. These graphs compare our first order differencing to seasonal differencing. In our top graph, you can see our original series, our graph of 2020 data with the first order differencing line, versus the bottom graph shows our original series again with seasonal differencing. As you can see, the bottom graph takes into account the seasonality and it is more in line with the original series than the first order differencing top graph. Now that we are confident we need a seasonal ARIMA model, we will run the Python ARIMA tool that can help us find the optimal model and parameter values for us to use in our forecasting. After running that, we are told a model of SARIMA 311-1017 is best, circled above. I'll explain this a little more. The 311 result makes sense with our first visualization because 3AR or P fits with the spike we see in the autocorrelation plot of the first level differencing. 1, which is our I or D, gave us a p-score of 0, and 1, MA or Q, would take more visualizations but fits with the understanding that recent events matter more for the data. The 1017 result is the calculated ARIMA hyperparameters P, D, and Q for the season of 7 days. Next, we put these values in the model and we'll look at some visualizations. Starting with the top left are our standardized residuals. The residual errors seem to fluctuate around a mean of 0 and with the exception of a few spikes have a reasonably uniform variance. The top right is a histogram density plot that suggests a fairly normal distribution with a mean of 0. In the bottom left, we see that most of the dots are in line with the red line. Any significant deviations would imply the distribution is skewed. The bottom right is a parallelogram, also known as our ACF plot, which shows the residual errors that are not autocorrelated. Any autocorrelation would imply that there is some pattern in the residual errors which are not explained in the model, so you will need to look for more X's predictors to model. Overall, it's not perfect as the spikes from the storm and other stochastic events seem to be throwing off some of our values still, shown with the heavy tail QQ plot, but our correlation is doing well, so let's go ahead and forecast. This graph shows the original series versus the model forecast. I calculated the root mean square error, RMSE, of these two lines as well as the R squared. Our R squared value of 0.71 is fairly high, especially for a forecast. It's worth mentioning that this score is based on a model trained on itself. The model generated the red line on the right, highlighted by the gray bar, which is a 14-day forecast for no actual data.